Let's go ahead and get started by talking about what we've got going on here. So last time we started talking about the magnetic field coming from a single moving charge, right? And before I get too much farther into this stuff, because we will kind of build on that idea, I'm not going to have my big long preamble this time around nearly as much. I want to jump into immediately a concept check to see how well we're understanding all of this stuff so far. Let's say I have like a classic bar magnet. So we can see north and south, and I take a saw to it and I just cut it right in half, or I snap it in half or something like that. What do we expect to see from each piece afterwards? Assuming that I'm not rearranging everything, I'm not just spinning some things around and moving them all about or anything else. Let's just say I have this thing. Let's even imagine that I had it something like this. Here's my big bar magnet. Initially, it was south on one side and north on this side, and then we cut it in half. What do we expect to see? Which of these 5 options appears to be closest to what we might expect? We're expecting here, because remember, as the way that this goes, north and south, these are not quantities, right? We don't measure how north a magnet is or anything like that. The general idea here is that north and south is really just a direction distinction. North and south tells us, and let me draw this thing kind of in a little bit of a wider space. So let's imagine we've got this kind of magnet. North and south tell us that the magnetic field goes this direction, right? It'll loop around from there, but it tells us about the direction of the magnetic field. The magnetic field is always going to go from south to north and then out from there, right? So it's not any sort of quantity to measure or anything else like that. But what this says is that this entire time, all along the length of this thing, the magnetic field goes in that direction. So if I split it in half, that doesn't change. The magnetic field would still want to go this way and still want to go this way. And this is a point that in the lab with today, we will show and demonstrate. So C should be our correct answer for this one. So let's try another one. Let's imagine we have a positively charged particle with a velocity going into the screen. What direction should the magnetic field be going? This is a right-hand rule kind of problem. I am expecting this thing to go up, but let's talk about that real quick. So, right-hand rule, we might remember that if we point our thumb in the direction of the velocity, then the magnetic field forms circles around that. So let's imagine for a second that that's a circle. Let's imagine that's a circle. My magnetic field, if I'm following right-hand rule, so again, you have to take this from your perspective here, but from my perspective, it's going into the page like this, so I'm expecting it to wrap around, from my view, clockwise. I'm expecting the magnetic field to look something like this. So, at this particular point that we're interested in, I'm expecting it to go up. So, speaking on that kind of lab idea here, this didn't work so well last time around, but I'm planning on this lecture being a little bit shorter with the idea here that you are going to go through and do a lab, right? And doing the lab, maybe. If you have all of the tools at home to do this lab yourself, I do highly recommend it, right? It's a really cool thing to do. It's a lot of fun to mess around with, but it does require some pieces that I'm not necessarily expecting everybody to have. So if you've got a couple different magnets and a compass and maybe a battery and a nail on hand, you can make this stuff work. But if that's not an option for you, that's no worry at all. Dr. Alexander walks through all of the demonstrations needed for this thing. So it's kind of written in such a way that it's maybe you're doing it. I kind of view this as Dr. Alexander's your lab partner, right? And he's the one running the experiment. You're the recorder working on the side, writing down everything that's happening. But go through and work on that one. He'll talk about some good details in that. There's an assignment up on Canvas for this one. But anyways, for now, if you are watching this sometime later in a recording or anything else like that, I would recommend doing that before going through the rest of this stuff. But for anyone here right now, let's just kind of keep diving into it. One of the things that I said in the last lecture, I ended up talking with some different students and have really decided that what I said was kind of wrong, and that I want to walk back that comment. I brought up this alternative version of the Beelzebub law, right, where it uses the R vector instead of R hat. Really, it's not any different, right? It's the exact same equation. It's just the difference is that R hat is defined as the R vector divided by the magnitude R. So if I was to plug in R hat to the regular equation that we see, we would get the same equation back out. And this is true just beyond this equation as well. We'll see some other places that this could be used. But I bring this one up because really the R hat form is more intuitive for seeing how the magnetic field changes with distance. But it's only really useful if you can immediately see where R hat is going to be pointing. If you have an R vector, let's make up some random example. If you have some R vector that is 1 centimeter, 3 centimeters, -2 meters. Let's stick with centimeters. Let's imagine this is my R vector though. Can I find the angle between that and this easily? No. Right? I could draw this out on a picture, but I don't think I'd be able to find this angle very reasonably well without trying to plot this out and really spending some time thinking about it. So in a case like this, where the angle between the two vectors is not immediately obvious, I would actually recommend taking this form instead. Because what you do now, and there's some slight differences here, of course. There are some slight differences here, but by taking this way, you don't have to start the problem by solving out for R hat first. And I know a lot of people have been getting stumbled up on 29.4 for this exact reason. Because in 29.4, particularly part C, they tell you that the R vector is equal to 0.01.01. And in that problem, R hat, maybe you kind of know what it looks like. This problem, I think you can draw a picture for it and actually find that angle pretty quickly. But if you're just looking at this immediately off the bat, your R hat vector would actually come out to be something like 0, √2/2, √2/2. Because remember, the R hat always has to have a length 1. So this is, I think, a little bit more confusing. I think it's a lot easier if you take this form right off the bat and just take the cross product between V and R. And you can kind of immediately jump to that. And again, I think the picture is a little bit easier, but this is a fantastic place to practice using this form of the equation instead. And you might find some different problems where if V and R are complicated, if the angle is not immediately obvious between those two, you might find it beneficial to take this form instead. Because again, really they are saying the same thing, right? Because it's just R over R cubed is the same thing as 1 over R squared, but it's that vector, whether we are just solving out for R hat in the first place or whether we're leaving it as the R vector and plugging that in. But both equations are trying to say the exact same thing. Okay, so let's go back and look at this, right? So the other Beelzebub law, right, the one that we were talking about a little bit more last time, where we use R hat instead, tells us about that relationship about how distance plays into the magnitude of the magnetic field. We said that if you have a point charge, and specifically a moving point charge, then the magnetic field from that point charge looks like this. Now, if you don't have a moving charge, you don't have a magnetic field. But what if you have a lot of moving charges? What do we do then? What if we had, say, a few moles of moving charges, like you might find in a wire? Well then, we've got to start to bring in integration, right? Anytime we have very many of something and we're looking for all of their contributions summed up together, we start to bring in integration. So let's talk about that. Let's imagine we have a wire with some current going through it. How would we describe the magnetic field from that wire? Well, I could say that every single little tiny piece of charge moving through the wire right now, every tiny piece of charge dq moving through the wire right now is contributing some little tiny piece of the magnetic field dB. Then that equation would say, okay, well, the contribution from every little tiny piece of charge looks just like the point charge equation, right? But now we would have to integrate over all of those pieces. And if experience has taught us anything, it's that integrating over every single piece of charge is not well defined. We don't really know how to do that. And I know I've brought this up, but we haven't known how to do that, and I don't suddenly have some special way to do it now. There's not a good way to do that. But let's look at some of these pieces here. dq times v. What is v? That's a rate of change of position. v is ds over dt. ds over dt times dq. Let me do some sloppy calculus things here, and let me shift that dt over. What if dt was under dq instead? ds, that is a little tiny piece of distance. Okay, well that's promising because I've solved integrals with distance. dq dt is just our classic definition of electric current. So if we were to have many, many charges, all moving at roughly the same rate, then maybe a better way to write the Biot-Savart law would be to say, instead of depending on dq, let's have it depend on the current, I, and ds as a tiny little length of that wire. Then to find that magnetic field, we would just have to integrate over the length of the wire, and that is something most of the time will be a lot easier to do. Let's try it in an example. Let's say I have an infinite wire, and I want to know what is the magnetic field at this point. So what I'll have to do here, step one, I need to pick my IDS, right? I need to say, okay, I know I'm dealing with a current. I'm going to take this equation, the Biot-Savart law for currents. That means I need some piece ds. And that is going to be a tiny little box, a tiny little sliver of my wire. Okay? Now we've got a lot of different things going on here at once, right? Now that I've got this thing, I could say, okay, well, every single little tiny piece of wire, IDS, grants me a little bit of magnetic field dB. Now there's a lot of terms inside of this equation that I don't know what to do with immediately, so we need to kind of tackle this piece by piece. Let me first look at R. If I were to make some sort of triangle out of this, if I am looking at this particular point along my wire, then I could say that this is a distance x away and a distance y away, right, along the axes, and that makes a right triangle. In my right triangle, my distance r is equal to square root of x squared plus y squared, or just Pythagorean's theorem to tell us what r is. So next, we need to start looking at some of these other pieces. We need to say, okay, well now ds cross r hat. I can draw out r hat, and I've got a good idea of where ds points. I know it's a little bit small, but let me draw it right here instead. So if ds points like this and r hat points like this, then this angle phi is the angle between them. Now that's fine, but what if I took, I don't know, this piece right here? Phi would change. So since it's a changing value the entire time, it's not just sufficient to leave that thing as is. I need to understand how it changes as I move along the wire. And a lot of this stuff is hopefully kind of familiar from when we were doing this with electric fields and with potential. But what I could say then, there's not immediately a relationship with phi and some of these other variables, but what I could say is that when I'm on one vertical half of the unit circle. So here's my full unit circle. If I have an angle theta versus an angle like over here, if they're exactly the same angle, sine of theta is the same for both of these, right? Or I could write this out if this was phi instead. But sine will give me the same value for each of these, so long as I am always on the top half, or so long as I'm always on the bottom half. Right? I can't do this left and right on the unit circle. It doesn't work with sine. But both of these would be equivalent in value. And that's an important deal because now I could say, okay, well, let me not take phi. Let me think about theta. Theta's inside my circle. Or not inside my circle. Theta's inside my triangle. If theta's inside my triangle, then I could say sine of theta is equal to opposite over hypotenuse, y over r. I found what R should be. I have a replacement for that nasty cross product. Because while I'm at it, I could say for good measure here that, well, I know the length of R hat is always going to be equal to 1. ds, the path, is always going along the x-axis. Might as well call that dx. Replace my sine of phi with, well, this kind of nasty fraction, but a fraction that we can deal with. And we've got a final expression for what that cross product should look like. Now, keep in mind here, what I've done this entire time is I've kind of said, okay, let's do all of these things, but focus on the magnitude. We need to use the right-hand rule to find the direction. So, let's think about this real quick. Before we go any further, what's the direction of my magnetic field? What do we think? In this particular case, yes, it is going out of the page. My charge, again, from my perspective, I know this gets mirrored and everything else, but my charge is going this way. So if my magnetic field is supposed to wrap around like this, I'm expecting that it, at this point P, B is out. So direction is handled. I only need to worry about magnitude, right? I don't have to worry about the fact that this is actually supposed to be a vector. I said, let's look at the magnitude only because direction's settled. So take this nasty piece, right? Now we've kind of simplified all of these things. We have replacements. So we come back to this. We put all of these things into my dB equation. I plug in all of these things step by step, and what I end up with is down here, which should look relatively familiar with what we have seen so far with electric fields. So we've got direction covered already. We have an expression for the magnitude of a piece of the magnetic field. All that we have left to do is integrate, and we have to integrate over x, and that's something I know how to do. So that whole step looks like this. I want to know the total magnetic field. To do that, I sum up every single piece of the magnetic field. I have a substitution for that because I don't know how to integrate that. So I plug in my substitution. I think about the bounds. Where am I going on the x-axis? I'm going all the way from negative infinity all the way to positive infinity. So those are my two bounds. Then I say, this is kind of a nasty integral, isn't it? What if instead of doing that, I just looked up an integral table instead? And that's exactly what we do. If you are savvy with your calculus, go for it. You know, this, I guess, isn't the craziest integral, but, you know, it's easy enough to just look it up on a table instead, or use Wolfram alpha. What I could say then, mu naught I y over 4 pi. Those are all constants. They can come right on to the outside. X is not a constant, so that has to stay in there, and this expression down on the bottom has to stay in. When I look it up on the table, I say, okay, we get this thing, which is not the worst thing in the world. Y squared, that's a constant. That can come outside. So it cancels out with the y on top. That's why we get this one down here. But then we say x divided by, okay, well, let me take a look at this. Infinity over square root of infinity squared plus y squared. Of these two expressions, which one's bigger? And by how much? Y is pretty tiny. In the grand scheme of things, infinity squared plus y squared, the y squared really doesn't matter. So then, this entire expression becomes infinity over the same infinity. It's just 1. And if I do that again with negative infinity, then it's negative infinity over infinity squared, which is negative 1. So 1 minus negative 1 is equal to 2. 2 times this cancels out one of the 2's on the bottom. I am left with this as my final expression for the magnetic field around an infinitely long wire. Which again, we don't have infinite wires, but just like last time when you talked about the electric field from an infinite rod, we don't have infinite rods, but if we're close enough that it looks really long, what difference does it make? The difference is negligible. So this is still a useful expression to have. We can still use this to find the magnetic field from very long wires, even if they're not technically infinite. So I've got some practice for you here immediately. I know this problem looks very similar. I know you can walk through all of the same steps that I just showed and get kind of immediately to the answer. But I want you to take this opportunity to go through and try these steps out yourself. Oh, why did I change Y to R at the very, very end? Well, because realistically, and I can jump to this picture, because I wanted to generalize this one. Could we all agree that if I spun this thing by 90 degrees, it would look exactly the same? If it was in the Z-axis instead of the Y-axis? What I'm really trying to say here is that it doesn't matter whether we're looking at this point, or at this point, or at this point, or at this point. The only thing that matters for the magnitude is your distance away from the wire. As long as we're dealing with an infinite wire, right? If it's not an infinite wire, that stuff's a little bit more messy. But we change it to R at the very end just to say, hey, this is a general case. Your distance away from the wire in any direction around the circle. That's the only thing that matters. Okay, but on this one again, my recommendation, try to go through all of these steps without looking at anything that we just saw. If you feel like you're stuck and you don't quite know the way out of it, look at what we have just done and then go back to your problem. Put that solution away, right? This is a great opportunity to try and write out a lot of these details and to solve some of these things out yourself. So I do recommend it. And I'm going to say let's take a little bit of time and work on this one. Then we'll come back together and take a look. I'll do a speed run through this one. Okay. So I think we're going to take a real quick look at this one, and I mean like a speed run through this problem. So I'm going to take a second copy of this one because I want one to be kind of clean that I can look at, and the other I'm just going to draw all over and make a huge mess out of it. So let's take this thing as we've got it, and we said, okay, from the very beginning, we're looking for this magnetic field. And I'll do this like I used to do a lot of these other problems. I'll say if I could only find the total magnetic field would be equal to summing up every single individual piece of the magnetic field. But then right off the bat we say, hey, didn't we look at this last time and didn't we already agree what direction the magnetic field should be going? Why bother with this thing now when we could just say, hey, don't worry about the direction side, worry about the magnitude, the direction is taken care of. Let me try not to erase the top half of that letter when I do that. So, okay, this might be a little bit easier to deal with then. So we say, okay, dB, we know that every single contribution to the magnetic field is made from every single little piece of the wire that carries current. So we've got all these pieces. Now, here's the thing. ds cross r hat, that's kind of nasty. So what I'm going to do is I'm going to go over to my junk picture, the one I'm going to draw all over. Let me say I was interested in this particular piece right here, this little tiny piece of the wire. ds points like this. R points like this, or specifically I'm interested in r hat, points like this. If we have some distance away from the wire, y, and so far we are x away from the origin, then I could say this angle right here, phi, if I wanted to find my value r, I would use Pythagorean's theorem. I would also say, okay, well, I'm very interested in knowing what ds cross r would be. Or ds cross r hat, specifically. So ds cross r hat, what I could say is that this is equal to ds times, well, the length of r hat is just 1, times sine of phi. Now, I don't know how to rewrite phi, but I can say that sine of phi would be equal to ds sine of theta if we had that instead. And we have a triangle, so we can find that instead. We can say that sine of theta is equal to the opposite over the hypotenuse. And again, r is changing with every single different point that we take. So I'm going to replace that with something else that tells me exactly how it changes. So we've got that, we've got that. The last thing that we can say is that ds is really dx. So my final expression, this whole nasty cross product, simplifies to be y dx over square root of x squared plus y squared. Okay, now that I've got that, let's go back to our main problem, right? Now that this thing is really nasty and hard to see what's going on, let's go back to our main problem and say, okay, well, now we found some replacements. Mu naught over 4 pi, that was never an issue. That was a constant that I'm going to pull out. I, that's another constant that I don't have to worry about. But the cross product and r, those are two things that I have to think about. And I apologize, there's still all sorts of stray marks in here. I don't know what it is. I am just trying to get to the end of the semester before my computer completely breaks on me. Now, my expression, though, as I'm putting these things in, I've got y dx, but I'm not doing from negative infinity to positive infinity this time. Instead, I'm going from negative L over 2 to positive L over 2. Try and see if I can get this thing to not do that anymore. Y is another constant, though, that I can pull out. But again, I'm going to look at the integral table for this, right? I'm going to say, hey, why bother with doing a bunch of extra stuff that I don't really need to? When I could just look it up. So when I look that up, I should find something like y over, not y, x over y squared, square root of x squared plus y squared, evaluated from negative L over 2 to positive L over 2. It doesn't simplify quite in the same way as before because, well, L over 2 is not that much greater than y. They're comparable values. But I can pull that constant y out. And what I'll be left with inside of my parentheses then is going to be L over 2 divided by square root of L squared over 4 plus y squared minus negative L over 2 over L squared over 4 plus y squared. Some things simplify here. L over 2 plus L over 2 is just L. I've got a common denominator between these two already, so there's no worry about that. My final expression, for the magnitude at least, is going to be mu naught I L over 4 pi y, and then times, here's kind of our remnant, try and make that look a little bit cleaner at least, our remnants of what's going on with this fraction. The fact that we have finite ends to our wire. All of that under 1. And there we have it. And then, of course, the direction, as we found it before, is just coming out of the page. So let's go ahead and keep moving on here. So, kind of as I was saying before, we can extrapolate the expression for the infinite wire to see that it's the same magnetic field all along the length of the wire in the direction given by right-hand rule. But there's kind of a fun thing. If we look at this, we might remember that when we went from a point charge to a rod of charge for the electric field, it went from 1 over r squared to 1 over r, which was kind of unique. Just in the same way, when we go from a point charge to a current-carrying wire, an infinitely long current-carrying wire, of course, our expression goes from 1 over r squared to 1 over r. There's a lot of similarities between these two things. The integrals look very similar. The final expressions look very similar. Can you tell that they're the same force, just with a little bit of a disguise over them? So, I've got a concept check for you, and this one might be a little bit more involved than some of these other ones so far. I've got two semicircle wires, and it's the same current going through this entire thing. But at my point P, what direction is the magnetic field going? It might help to write down some expressions for this one, but think about this a little bit. What's going to happen here? So this one's a little bit difficult to see at first. And this is not one that I'm really going to justify just by looking at it. In fact, I want to think about how to solve this one out real quick, actually. I want to say, okay, well, for the sake of it, let's imagine that we're looking at a tiny piece of one of the wires. dB, that expression, comes out to look like this. Now, a nice part of this is that ds cross r, because we're dealing with a circle, we can see for either of these lines, that's a right triangle. That's a right, not a right triangle, that's a right angle. So that means that the cross product is, well, it's just ds. Right? So this ends up looking like this. ds is just the total length as we go around. So since we're dealing with a half circle, since r is constant, since I is constant, ds is just half of the circumference of a circle, pi times r. That means my final expression for the magnetic field, mu naught I, pi times r, one of the r's cancels out and the pi cancels out. That's my expression for the magnetic field from one of these wires. But I didn't specify which wire. That's the expression for the magnitude of the magnetic field from either wire. Because they're both semicircles, because they both have the same current, all that good stuff, I've got this. So what we see here is that how large this semicircle actually is, how much wire length there actually is not the factor that comes into play here. It was there, but it kind of got eliminated by the fact that we had a 1 over r squared, right? That detail is tucked in the fact that we're left with a 1 over r expression. But because we're left with a 1 over r expression, the part that has the smaller radius is going to be the dominating part. And because of that, we expect the inner wire to be contributing more to the magnetic field. So we are going to follow, the right-hand rule would tell us that this part is coming out of the page. This part is going into the page. So we expect at this point right here, we're going into the page. So, let's imagine. We've got two very long wires with current going through them as given by these little arrows inside. Right? So the top wire, it's coming towards us. The bottom wire, it's going away from us. What is the magnetic field at each point, A, B, and C? And I'm going to give you a hint here. The way that I would really recommend solving this is to draw out a complete picture first. Draw out what the magnetic field would look like coming from each wire. Save yourself a lot of work. All right, let's start taking a look. So, I said this before, if we start by drawing out the magnetic fields, we'll have a much better time with it. So the first thing that I actually want to do here is I want to take, oh, that's not at all what I meant to do. I meant to select that. I want to draw this thing out, and I'm going to draw this thing out kind of like this for now. So that's roughly a circle. Now, right-hand rule would tell me that my current coming towards me would produce a magnetic field from my perspective going counterclockwise. So my B field for this one would go like this. That tells me that my magnetic field at point B would be going exclusively in the x direction, whereas at A and C, it's a circle going out, right? So I'm expecting this thing to go kind of like this, and I'm expecting this thing to go kind of like this. So what's a physicist's best friend when they're trying to avoid doing work, especially in electromagnetism problems? What do we remember from all of these chapters that we've looked at so far? Whoops. What's the greatest tool that we have at our disposal? Any guesses? Symmetry is exactly correct. I love symmetry, right? It makes all of these things so much easier to do. So what I'm going to do is I'm going to look at this one and I say, okay, well, I'm going in the opposite direction, right? The current is going in the opposite direction. So now I'm expecting my magnetic field to be going clockwise. But that's okay because we're looking at different orientations. The wire is on different ends of my 3 points. So here at point A, I'm expecting this now to be going like this. At point B, I'm expecting it to go like this. At point C, I'm expecting it to go like this. Let me draw that a little bit better at least. Something, whatever. Drawing down and at an angle is not a good skill of mine. But anyways, we can kind of see this. What we've got in here is a bunch of different symmetrical arguments. And on top of that, these are the same currents. The top wire and the bottom wire are the same current. They're the same distance away from all 3 points. There's a lot of similarities between these 2 contributions. Even more so, let me look at point A and point C. Those are symmetrical. I'm going to make the argument right here that A and C are going to have the same direction and magnitude of the magnetic field. More on that, they're only going to have an x direction to that magnetic field because I can kind of see from my picture right off the bat, the y components cancel out. So let's start there. Let's say parts A and C from one wire. My contribution then would be mu naught I over, and I'm forgetting what constant I'm actually supposed to, 2 pi r. I was like, I know it's not a 4 pi r, but I don't think it's just over r. So that's my contribution from one single wire. My distance away r, in this case, I'm 1 centimeter up, 1 centimeter over for each of these. So current is 10 amps. R is going to be 0.014 meters. Pythagorean's theorem for that one. But now I do have an issue. I can't just throw this thing in there immediately. I need to split this up in x and y components. But if I know that I am 1 up and 1 over, I can say that for either of these, the angle off the x-axis is just 45 degrees. So my x component is going to be mu naught I over 2 pi r cosine of 45. My last step is to say, hey, well, I've got 2 wires making exactly the same contribution because they have the same current, the same angle, the same distance away. B total is equal to mu naught I over pi r, because I've doubled up 2 wires, cosine of 45. At the end of the day, I'm expecting this value to be 4. Oh no, that's not quite right. What did I have here? Whoops, not 4. That's the next one. I was going to say something immediately sounds wrong here. 2.006 times 10 to the negative 4th I hat Tesla. That's what we've got for both of those points, for parts A and C. I expect the exact same magnitude, the exact same direction. Now, part B is even easier, because what I can say is, hey, I'm 1 centimeter away, and the X component is the only component. There is nothing else to be worried about. So again, I'll make the argument, one wire would just be this quantity right here. Now, current, I should have said theta, is equal to 45 degrees. Another part for part A. But this is 10 amps. This is 0.01 meters. So B total, all the wires together, is just this. Plug everything in. What we should find at the end of the day is 4.01 times 10 to the negative fourth I hat Tesla. Or if you're interested in the Canvas answer, we have this in millitesla instead. So that's 0.401 millitesla. And that's what we've got. We've got just a couple more things for today, and then we'll be done a little bit early. So, quick concept check. If I have a ring that has some current going through it, and again, the current is specified by the direction inside of the wire, which side of this loop do I expect the north magnetic pole to be on? So, let me look at just a single piece at a time. Let me say, let's look at this right piece right here. If it's coming at me, I expect my current to wrap around like this, counterclockwise. If it's going away from me, I expect it to be going clockwise. If I were to expand this out for the entire ring all the way around, and I were to draw these circles a little bit bigger, I would expect my magnetic field to look like this. And then remember, north and south are really the orientation. So the south is where the field lines come in. Whoops, I just said the opposite thing. The south is where the field lines come in. The north is where the field lines leave. So we're expecting the north magnetic pole to be on the bottom side of this current loop. So I've got one more whiteboard problem for you, and I've actually kind of already shown you how to solve this one. One point that wasn't brought up before, though. Nobody asked me about this one. On this problem, what about these two pieces? Why didn't I say anything about those? Are there any guesses? What do we think? Did I just forget to remember those? That's exactly right. Sine of 0 is 0, which is kind of a disconnected way to say that, but what we're really saying is that the current, my path ds, goes in the same direction as r hat. And for cross product, that means it's 0. There was no contribution from these points pointing directly towards point P. So, if we are looking at this whiteboard problem, I can immediately off the bat say, hey, this point and this point, or these lines, these segments of wire, these don't make any contribution either because ds and r hat point in the same direction. And for a cross product, that means 0. The only part we need to worry about is this circular portion. So, I'm going to give you guys a little bit of time to work on this one, and then we'll look at it together. Let's go ahead and take a look at this real quick. So, and this will be a real fast one, because again, I kind of already said, we've kind of already solved this one. But let me think about that for a minute. So if we were to line up the exact same details as before, right off the bat, we can immediately tell the direction. We could say for any of these points, right-hand rule would tell me that it's coming towards us on this side, away from us on this side. So point P being on this side should be going into the page. Now the direction's taken care of, let's talk about magnitude. What we could say is that every single piece, again, u0 over 4 pi, and again, I'm drawing out the complicated one, but we're going to try and simplify this immediately. R is a constant. We're the same distance away, capital R, the entire time. ds cross r, let's look at like this exact point, for example. ds goes like this. R hat goes like this. That's a 90-degree angle. As we go all the way around, it stays a 90-degree angle. R hat has a length of 1, so it doesn't matter. It doesn't contribute anything. So this entire mess actually turns out to be mu0 over 4 pi I ds over capital R squared. Now, I just need to think about ds. I is a constant, R is a constant, mu0, pi, constants, right? Or numbers, realistically. So for all of these details, what I can say then is, all right, well then ds is really just my entire path length. My path length is however long this piece of a circle is. That's my total S. And anytime we're trying to talk about a piece of a circle, we can write that out as theta times r. When theta gets to be 2 pi, we get back 2 pi r, the circumference of a circle. But this is it. If we were to integrate the entire dB, ds just becomes s. So b mu0 I pi over 4 pi capital R. Because one of the r's got canceled out. And that's it. R hat was pointing this way, but in this cross product, because ds cross r hat is equal to magnitude of ds times magnitude of r hat times sine of 90, and that's always true, right? For this semicircle, it's always an angle 90 between the two. So this is 1, and this is 1, and I'm left with just ds. So I think with that, we'll close out 29-2.